So I have these three components in here. So it looks like you've added some notes in here. So object one, you want to basically with a 1-inch diameter end mill, and then you want to cut the tenon with a 350 millimeter saw. Is that right?
Yeah, those numbers are fairly arbitrary, but they reflect
Okay.
what, you know.
So you're talking about these features in here, cutting with a saw blade, something like that. Is that right?
Exactly. Yes. Yep.
Okay. So basically, you want to come in at an angle and just basically cut across. Is that how you want to cut it?
Yeah. I mean, I believe with that saw that both the vertical and the horizontal cuts could be
Okay. So
made
basically,
potentially,
okay.
but obviously the horizontal cut is not a 5-axis
Yeah. Okay.
thing.
Mm-hmm.
Yeah, 2-axis thing.
Right. The horizontal cut will be, the tool will be parallel to the XY plane in here.
Yes. Yes.
Like the diameter of the cutter, and then for this, you got to figure what the angle is for cutting it out. Okay,
Yeah.
makes sense. And looks like you got this pocket in here that you want to cut with a, with a tool. All right.
Exactly.
And then on this particular part, it says rotate spindle to horizontal and mill with a profile knife. So when you say profile knife, are you talking about like a form tool? Is that what you're referring to?
Yeah, I think essentially the profile of the molding itself will come from the knife. It's not going to be machined as one would do with a three-dimensional, with a 3D program with the ball mill. Essentially,
Okay. So you have a tool that basically can follow this contour, and then you just want to go in like one pass around it.
exactly. Yeah. Yep.
Okay. All right. Okay. So that would be like a user-defined tool, and then you can do like a two-axis operation or something, or like an engraving or one of those operations, because form tools or user-defined tools are limited to two-axis operations, and like maybe like engraving operations with it.
Well, yeah, and in fact, there really isn't any need to have that profile in place. I simply wanted to
Okay.
have the idea there. I mean, essentially, the head needs to rotate to horizontal, and it needs to, as you say, follow essentially a two-axis toolpath.
Okay. So in this case, it wouldn't be a two-axis, because if the head is rotated, then over here, this would be like a Z would be varying in here, right? So because the cutter, if the tool is parallel or perpendicular to this face, then it's basically, this is a Z-axis motion. The cutter would be going in and out as you're following this bend over here.
Yes, I believe we're saying the same thing.
Okay. So in that case, you can do like an engraving operation, which can follow along like a 3D curve. Okay, so let's go ahead and see how best we can program these, and then you want to drill these at a 7.5-degree angle, so the tool is basically at an inclined angle. Is that right?
Exactly. Yes. Yeah.
Okay. All right. So we'll start with first programming this particular feature in here, and we'll then go ahead and program the rest. So would it be okay if I can just go ahead and hide these two features for now? We'll just go ahead and
Oh,
hide
absolutely.
these two.
Sure.
I'll just go ahead and set up the machine tool. So go to the Program tab, click on Machine, and then this is where you define the machine tool. Number of axes would be 5. You pick the configuration as head. This is when the head rotation is on the spindle, and the part remains stationary. So you pick head. We could also do a combination of table and head, or a table where the part rotates on like a trunnion type of machine. And on a head configuration, typically you would like to want to output everything in the world coordinates, so which means all the rotations, when the tool is moving in and out here, it's going to transform this into the world coordinates. So if this is going to be Z motion in the rotated coordinate system, technically that would be a world Y coordinate move as the cutter moves in and out while you're milling this pocket. So you want to clear this checkbox. Then you pick your rotational axis, the primary axis, your secondary axis. You can also put in the limits for the primary axis. It could be no limit, which means the C axis can rotate 0 to 360, but then the secondary angle can be set to be like anywhere between like minus to plus 120 or 135 or however far it can tilt, right?
Okay.
So that
Yeah.
goes right in here.
Yeah.
So I could say minus 120 to plus 120. And then if the gauge length needs to be compensated in the CAM program, then you can put in a gauge length, which is the distance from the pivot point, as you see in the graphics image, the pivot point to the spindle face is what you put in here, plus the tool length gets defined when you create your tools. So if the controller can handle, like a TCP, then you don't need to double compensate, so you can just leave that as 0 in here.
Okay.
All right. So the next step is basically selecting a post processor. We currently have all of these posts that you see are for 2 and 3 axis. We do have developed posts for 5 axis as well. And I'm going to select a post from the list here. Would you happen to know the controller that you're leaning towards or looking at?
It will be OSI 5 axis.
Okay.
Yeah.
So I have one for on-through here, and there's also a generic OSI 5 axis. I can select that, and we can also modify the post, and you can define your primary and the secondary axis. This post is set to do C axis and the A axis for secondary. We can change it to B or whatever the axis codes or definitions are.
Okay.
And we can configure the post in here as well.
Okay.
So I'll just pick the OSI post, and we can check the units that it's currently set up for. It's set to inches. Some controllers use G70 or G20 for inch. Millimeters will be G21 or G71.
Okay.
Okay, so you're now ready to define your stock material, so we can go ahead and do a box stock. And I can ignore the sketches or curves and then define it based on the extents of the model. So we define the machine, we got this post, we have the stock defined. The next step you want to make sure is the orientation, so looking from the top view, is the part in the correct intended orientation for machining. If it needs to be rotated, you can rotate it in Rhino or use the orient part feature in here to rotate it. Now, one of the things we want to do is we want to machine this pocket first, so I can go ahead and orient the coordinate system to be normal to that face. So we can add a new setup. Setup defines an orientation. So I want to make sure that the z-axis, which is the blue arrow, is perpendicular to this face. So in this particular example, by looking at the model, this looks like a 90-degree rotation. You can either use the spin angle to rotate it. You can say you can rotate it right there. And you can use these controls, again, to rotate it any way you want it. So basically, we rotate the coordinate system normal to this face. Or you can even pick a surface. You can say select a face. I can just pick that face, and it'll automatically determine based off the normals, and then you can further rotate it as you need it.
Okay.
Okay. So we've rotated the coordinate system for machining. The next step is we want to mill this pocket in here. So I'm going to get some measurements in here to figure out how big of a tool I can use. I'm going to use distance measurements, and I'll just measure these 2 points. So that's about 2 inch. So you can probably go with a 3/4 inch end mill or even a 1 inch end mill, depending on the size of tool you want to use. So I'll just do a pocket operation. And then for the features, I'm just going to go pick these 4 edges in here. Or I could pick the floor of the pocket as well, which is at the bottom. And then grab a tool for it. So we'll just use a 3/4 end mill. Unless you want to do a 1 inch, I can go back and change this to a 1 inch cutter.
No, it's academic. It's quite all right. It doesn't.
Okay.
Yeah.
So I could change this right in here to save as new tool. So we have a 1 inch cutter. Feed speeds. You can notice that the clearance is parallel to the plane that you're in. And if you want to change that here, I can change it to stock max plus 1 inch or even 2 inches, how far you want the clearance to be out.
Okay.
In the cutting parameters, you can specify the tolerance, the stock allowance, your cut patterns. In the cut levels, you can specify how deep you want to cut. I can actually pick it for going from here down to the bottom edge. So it uses a linear distance based on the orientation that you pick. You can put in your depth per cut. So let's say you want to go 2 inches per pass. You can set your entry and exit parameters, and then finally you pick generate. So I want to make sure my tool is long enough. So I'll change the tool length to be 6 inches. I'll update the tool, generate the path. So we have a pocket operation programmed in here. So when you run a simulation, you'll notice that the tool is tilted in the orientation. Okay?
Yes, I mean, it's a very familiar operation to me. I obviously do a great deal of 2 and 3 axis work, and I simply did not understand that it was possible to adjust the orientation of the.
Yep, that's how you do it. The next thing we want to do is probably try to mill this with a, we don't define a saw blade cutter. The closest tool will be like a face mill. We can define it and then program this here. So what I'm going to do is prep this part here. So I'm going to duplicate edge, and maybe I'll just put it on this new layer. I'm going to extract this edge, also extract this and this edge in here. Okay, so I basically extracted some sketches from the model.
Okay.
Okay. And I want the cutter to come in at this angle to cut this out, and I can compensate based on the thickness of the cutter, what I have here. I can basically select these objects in here, and I can also move it out by, however far based on the thickness of the blade, so we can do an engraving operation for it.
Okay.
And also, I'm going to check the direction in here of the curve. So you want it to start cutting from this direction, following this, and then retracting, or you can flip the direction in here, going from this direction in here.
Okay.
Now you can also increase the length of this here. So I can create a line. I can do an extend, and you can pick the curve to extend in here, and you can give it a distance how far you want it to extend out. I can say maybe 10 inches, for example, right? So I can do the same thing here. Okay, so I've extended the curve. Now what I would like to do is basically add a new setup in here. And I want to put the setup to be normal to this face. But then I want to go ahead and rotate it so it's actually parallel to the face. The Z is parallel to this face, right? So I'm going to go back and rotate it about Y by 90 degrees. So you now notice that the tool is tilted to an angle right there, right? And
yes,
I'm going to define a tool. I can use a face mill tool. I can define a tool like a face mill. And I would like to go ahead and give it a diameter for the tool. So do you remember what was the tool diameter you were referring to here?
350 millimeters, which is about 16 inches.
Okay, so 350 millimeters would be, I can do 350 divided by 25.4. So that makes it about 14 inches.
Oh, only 14? Okay.
Yeah.
Could be.
And then I can give it a shoulder diameter. I'll just put in 1. Flute length, the thickness of the cutter, maybe like a, 100 thousandths or 1/8 of an inch.
Sure. Right? Yeah.
And then the shoulder length, I can give it tool length. I can give these parameters in here. So it's defining a tool right there. And you can see there, since it's a fairly large, the preview looks really small over there. So I'll call this, face mill 350 mm.
Sure.
And then I'll save this up right here. Save as new tool. Okay, so we've defined the tool. Now what I want to do here is go ahead and offset this by a 1/16 of an inch, so the center of the cutter can follow this.
Okay.
So I'm going to use a gumball, and I'll right-click and say Align to Object, and I'll offset it out. I can do an Alt and then offset it out by a 1/16, since I gave it a thickness of 1/8 of an inch, right?
Yeah.
So I offset it out. And now what I'm going to do here is basically program an operation called Engraving with the 2-axis engraving. I'll pick this as the curve. You can see that I've already defined my entry and exit as well in here.
Yeah, I see that.
Now, one of the things I could also do here is I can extend this out. So let me go ahead and save this out. I'll just do an incremental save. And I'm going to extend this out also by the tool radius. So I'm going to pick this, and I'll do a scale, 1 dimension. I'll pick the midpoint of this line. Then I can extend it out on both sides, right?
Yeah. That's
so
perfect.
For the cutter to be well clear of the part, so I can pick how far I want to extend out. So now I can go back into this operation in here. I may have scaled the wrong one, but I'll go back and move this out by 1/16 of an inch. Okay. So now I'm going to go back into the engraving. Just pick this curve. And then for the tool, I'll pick the 350 millimeter face mill. Feet and speeds will load it from the tool. For the clearance, I'm just going to do an absolute Z and just pick that point right here.
Okay.
Okay. And the cutting, I don't need to put in any depth in here unless you want to go in multiple steps. Also, I would want to offset it out by the tool radius up in the Z. So you don't want this is the center of the tool that's going to be in here. So you can either do if it's going to be the tool center, I want to make sure that this is offset by half of this distance in here. So 13.77, so let's say it's about 14. So half that amount is about 7 inches.
Mm-hmm.
So that's where you want the geometry to be. So now when you go back and edit this here, we'll set the clearance to absolute, and we'll just pick that point right there, generate it. So that's going to give us a engraving pass. So let's go ahead and take a look at this, the simulation. You'll see that the cutter, in this case, it's coming down at that angle right there, but you want the tool to be at this 90-degree rotated angle in here. So I'm going to go back to the setup. We'll put it to normal to the surface. Okay? And now I'm going to go back into the clearance and make sure the clearance is right over here. Generate it. So now if you take a look at your simulation, you see how the cutter is following right there?
Yeah.
And you can extend this however far you want it. I just showed you as an example, so to be fully clear of the material.
Yeah, that's perfect.
So that's how you can program a face mill to do like a saw blade operation. You can repeat the same for the other side once you flip the part over.
Right, yeah.
And now when I go back in here and post it, do a post all, RhinoCam takes care of the computation of the angles. So the first one says A minus 90, C 180. And then you can look for the next one in here, A minus 90 and then C 45.
Yeah.
So those are the two angles to get to that. The saw blade and then the other one. So that's how you go about programming these.
That's great. Could we return just very briefly to the mortise? In order to change that setup, can you show me again where you went to do that?
So you go into the setup right in here.
Okay. Yeah.
You can add a new setup. You can create additional setups, and you can choose how you want to orient it. So you can say you're based on a normal to a surface, a planar curve, which is a planar sketch or curve. You can even put it to an active construction plane in Rhino. You can rotate using the spin controls as well.
Okay, great. Yeah, I think I can work with that. I'll just need to spend some time with it, but I was ignorant of that ability.
Yeah, setup basically defines an orientation for machining, and it's typically very commonly used in index machining.
Yeah.
So that's how you typically go about programming this. Now let's look at the other samples that you have. So let's go ahead and take care of this one here, and then we'll work on this the last one. So you want to drill the holes but you want it to be at an angle. So let's go back and add a new setup in here. We'll put it back to the machine tool coordinate system orientation. So it'll put it back to the world. And now you want to tilt it at an angle. So you want to do like a 7.5 degrees. So I'm not sure if the holes are tilted. No, not
They are.
yet, right?
They are
They are?
tilted. Yes. Yeah.
Okay. So let's go ahead and check in like a ghosted view. They're at 7.5 degrees.
That's not the right perspective. You'd have to go from the right side. Yeah, there you can see it.
Okay, so this one right here?
Yeah.
Okay, so let me go ahead and just hide this one right here. Okay. So we want to machine these slots. All we got to do is basically tilt that to that orientation. So in this particular case, I want to rotate it. I can take the setup in here, rotate it by 7.5 degrees about the x-axis, and I can say minus 7.5. And you'll notice that the coordinate system is tilted, right?
Yeah, I see it.
Okay, so now you can pick these geometries and then program the toolpath for it. So you could use a two-axis operation. So if you want to basically drill the holes, you could just do a drilling operation here. But this one is a slot, right? So what you have?
It is, yeah.
Okay, so you could do a slot machining operation in here to program this. You can pick those edges and do a slotting operation. Or you could, if you want to do a drilling operation, you can just do a hole machining drill. And all we need is to pick a point, or we can pick a closed chain in here. I can use the chain selection command in Rhino. And then I can pick a tool. I could just go with an end mill for drilling. And I can put in the depth in here, how deep I want to cut. And then I can specify, then pick generate. So here it's actually trying to drill in each and every point because it's not continuous. So what I could do here is maybe put in a circle, or I could do what is called duplicate the border and then pick that from the model.
Yeah.
And I can go back into the drilling operation in here and then just pick this one. Pick the close curve. So it's going to try and drill it, at the center, at the angle. So if you go ahead and recreate the stock in here, I'll do a box stock. And let me move this to the top of the tree here. So you can see that the clearance is not correct, what I have here.
Yeah.
Because I brought in the clearance from a previous setting. So I'm going to say stock max plus a distance. Or I could even pick a point in here for the clearance height. So I can say where I want the clearance to be. You can also change the clearance to be an absolute Z height. You can pick an absolute Z and then you can just say right here. Or you can change the height for the clearance. And generate the pad. So now you can see it's in drilling at an angle.
Yeah.
If you want to change this to a deep drill or a peck drill, you can change it to a deep drill. You can specify an increment, and that'll give you a peck drill cycle. And typically when you do it inclined planes, the controls cannot handle them as drill cycles, so you got to output them as linear motions. So now when I post this out, it's actually going to output, you can see the angle that's computed, 7.5 degrees, and you can see outputting them as a bunch of linear motions, point-to-point move. So you could, likewise, you can program the other holes as well.
Yeah, wonderful.
So I can either use it in a same setup. I can have a second operation. And the reason I'm programming them separately is I can alter my clearance height based on the model here. So I can basically increase the clearance height as needed. So now I got 2 operations.
Why would you consider it necessary to change the height?
So if I program all of these in one operation in here, let me go back and then I'll pick multiple of these. Because it's at an inclined plane, the clearance will be at the inclined angle to accommodate for all of them. So your clearance is going to go really high when you look at the clearance. So you may have to account for all of the model, all of the holes. You may have to increase the clearance because you're at an angle. So the clearance is going to be much higher over here, the farther away from the incline. Do you notice that, sir?
I do. Yeah. Yes.
Because the clearance plane is parallel to the tilted plane or the setup that you have. So in this case, it's the retract motions are going to go much higher. So to make it efficient, we can just break it up into multiple operations.
Okay. I understand. I understand. Yeah.
So rather than having to retract all the way up to this point. So now when I post these 2 out, it still maintains the same orientation, 7.5 degrees. Okay?
Yeah.
All right, now let's take a look at the last one in here. Okay, so let me go ahead and hide the rest of it. Okay. Now, in your notes, you mentioned that you would like to rotate the spindle to a horizontal and mill with a profile knife. So when you say horizontal, you want the tool to be perpendicular to this face right here?
Yes, exactly. Yep.
Okay. So the process would be very similar. So you can add a new setup in here. And you can say you want to rotate it by 90 degrees. This would be on a Y. You can also tilt it about the Z if you need to. So now you can see the Z is perpendicular to this face. So now if you want to use a specialized tool, like something like that has this form in here, right? 1/2 of this right here.
Yes, yeah.
Okay, so what we would have to do here is I would have to create these, I would have to form the profile in here. So
well, I really don't think it's necessary to do that. I mean, I would be interested to see it, frankly, but for purposes of machining, I simply need to know, how to.
What kind of cutting strategy you want to use?
Exactly. Yeah. I mean,
so what I'm going to do here is I'll just pick these edge in here, and maybe just for the purpose of our demonstration, we'll just do a flat mill.
Yeah.
And then you can probably, create a user-defined tool to program it. So I'm going to pick these edges in here. Just these edges right there. I'm going to press Enter and then join them together. And now I'll basically, let's say I want to use a 1/2 inch tool. I'll move this up by like 1/4 inch up in the Z. Okay? You see the curve right here, sir?
I see it. Yep.
Now I can actually use an operation called Engraving. And this would be able to follow the curve. Now, since this is going to be like a 3-dimensional curve, it's going to follow that for us automatically. And I can specify the clearance right here. And I'll generate the pad. So let me create a stock model here, box stock, or I could do a stock from selection here. There's stock from extrusion. That'll be a nice one to do. So let's do a duplicate face border. I'll pick the bottom face. So let me do what's called a curve boolean so we can get the outline around the part. Or we can do mesh outline. Okay, so we got this here. I'm going to do a stock by extrusion. So there's the stock. I create a custom shaped stock as you see it right there.
Yeah, that's great.
And then this engraving, I've just done it in one path. You can see now basically the curve. The tool is following the curve. Do you see that, sir?
Yeah, I do. Were this to be um,
Is this how you plan to program it, but use a
well,
form tool?
I'm not sure that that would work. Can you rerun that simulation in the top view?
Yes. Let me go to the top view here.
The tool is remaining.
Horizontal to the face, but then
Yeah,
it's moving in and out, following this curve.
right. Were we actually to be using a profile knife and machining that, the tool would need to be changing, would have to follow that.
Okay, you want the tool to be normal to that. Okay, makes
Exactly.
sense.
Yes.
Okay,
Yes. That's right.
all right. Okay, all right, makes sense. So what we would need to do here is let me use a different technique in here. So I'm going to do a technique. Let's go ahead and so this model here, I'm going to create an ISO curve, extract ISO curve. I'll pick this surface, and I'll use the midpoint right here. And then I'll go continue along. I'm just going to use this surface as an example here. So let me repeat that. So let me go ahead and explode this model in here. So what I'm going to do is basically pick these surfaces. So I'll use this surface so that the tool will be normal to that surface.
Okay.
So I'm going to use this as an example in here. I'll pick these surfaces. So that would be a 5-axis toolpath method. It's called 5-axis surface. We can do a 5-axis curve projection machining. So let me invert the rest and hide it for now.
Okay.
So I'm going to go ahead and extract a curve. I can pick a curve right here. I can do a duplicate edge. I'll go pick these curve in here. Just pick the bottom edge around the part. Okay. So now what I could do here is I don't need to tilt the coordinate system when we program a simultaneous 5-axis operation, for example, like a curve projection. We pick the curves it needs to be projected, so I'll pick this curve. And then for the surfaces, I'm going to use these surfaces in here. So and then I've got to check the normal orientation. Make sure the normal is pointing in the correct direction. You can see it's all pointing down towards the wrong side. So I'm going to say flip all normals.
Okay.
I can see the normals are being flipped. And you can pick a tool for it. Set feet and speeds and clearance. We can do a planar clearance. And then for the cutting parameters, you can put in a projection distance and generate the pad. So in this particular case, you will notice that the tool, let me run a simulation, is being normal, and you can see it changes the orientation as you're cutting it. So this is like a simultaneous or a true 5-axis machining.
Right, and that's what would be necessary.
Yep. So this can only be done with standard tool types like flat mills, ball mills, corner radius tool. You can't use a form tool, but you can actually program it with like a flat mill, and then you can swap it out with any tool that you like.
Right. Good.
Now when I do a simulation in here, you'll see that the tool is being normal to the surface at all times.
Yes. The only thing is that the angle of the tool
Needs to be horizontal.
would want to be horizontal, right?
So what we would have to do here is we would have to basically pick this edge. I just use that as an example, so it's using the normal base of this. So had I used the normal base of this face, then it would have been parallel to that. So I can, do the same here. I'll do a duplicate edge. And I'm going to pick these edges in here. Join them together. And if I go back in here and pick this curve, and I'll go pick select surface. Let's say I pick these surfaces. So you need to just basically model like a drive surface.
Yeah, I see.
Tool to be normal too. And now generating this path. You'll notice that the tool is normal to that, and it's actually flipping the angle because it's right over the edge. So I can move this curve slightly below it, and you'll see it basically is normal to that.
Okay.
So if I take this curve in here and slightly drop it down in the Z, and I can go back and regenerate this now. Yeah, it should. It's probably flipping that over because the normals is changing right there. But
yeah.
Kind of get an idea how it works, right?
Yes. Yeah, I think that's, I understand enough to be able to.
Okay, so that would be a surface normal machining operation. So now when you post this out, curve projection machining, you can see the A values are changing, and then also it rotates as you're cutting it. See, the C is rotating right there.
The C is rotating, yes. Yep, I see that. Yep.
And the A stays at 90 degrees.
Excellent.
Okay.
That's.
Would that answer your question, sir?
It does. Yeah, that was extremely helpful.
So you could use any of these simultaneous 5-axis methods for different type of applications. And the type of tools that you can pick on these 5-axis simultaneous methods are limited to ball mills, flat mills, corner radius. You can have taper and chamfer tools. So you can create custom or form tools which can be used in like 2-axis operations like these form tools.
I see. Okay.
Is there anything else that you'd like me to cover during this demonstration today?
Well, that was extremely helpful. I think that ultimately, one question I did have regarding the, I believe it's in the machine, you have, excuse my lack of vocabulary, but you have a number of simulated machines that you're able to call up and actually. Do you know what I'm talking about?
Yes, you're referring to what's called a machine tool simulation, which
right.
We do that by going to like a load from file, and then we can pick a machine tool from the list here.
Yeah, I think that's what I was discussing. Is that something which
we can certainly build and add the machine tool models. So here, this is just for the purpose of visualization here.
Yeah.
simulation that you can see. It's not going to provide you any collision with the machine tool or any of those. It's just to for viewing and make it easier for you to see how the tool is tilting as you're cutting it.
I see. Okay. It's it's probably
We
not
would need the
necessary.
model, the machine tool model in here, and then we can add it to the list. So we need the different components like the x-axis, your z-axis, your c, your b-axis. So basically, these are all converted to an STL file, and then you can save it in this directory, and then you have an XML file which establishes the relation and the kinematics in here.
How frequently do you think people use that? I would think that if you're able to simulate the tool accurately, that there isn't a great deal of need to have the machine on there as well.
So this will give you basically it's same as your it's like your cut material simulation. Instead of the tool, it basically shows it with the machine tool instead of just being the cutting tool. It shows it with the machine tool.
Yeah. Okay. All right.